very glad that we have a good number of people on the call joining us for the second webinar on the outcomes of the GloBE project Tuesday this week. And we discussed the measurement campaign, as well as the sort of background to the project as a whole and what we're trying to achieve. Today is much more focused on using the outcomes of that measurement campaign to try and learn something about how to model and account for blockage when looking at energy yield predictions from large offshore wind farms. And I'm glad to say we've actually made a lot of progress on through the project. So to set a bit of a teaser for later on, we actually do have a joint statement reflecting a consensus coming out of the project. So what we're going to talk through today is the process by which we got to that, and then the headlines of those conclusions, and point you at the document itself for future reference. Just as a reminder from the session the other day, GloBE really had 5 objectives overall. So starting from the right-hand side here, we were ultimately looking to increase confidence in energy yield predictions for large offshore wind farms. And the measurement campaign on the far left, which we talked about on Tuesday, was a necessary step for achieving that, but it certainly wasn't sufficient. We had to use that data set to test hypotheses on what was going on with blockage, what the physics of the problem really was, and to test different ways of modelling it, and then build some industry consensus around that, such that we converge on a set of tools that can be shown to work, and a set of methods for accounting for that in the energy yield prediction. So today it's really all about that industry consensus building part of the process. I showed this horrible diagram the other day, which really illustrates the complexity of the project setup within GloBE and the number of different organisations involved. The part I want to highlight just now is that little box in the bottom right, the independent technical review group, where we have a number of the key players in the industry coming together to inform this consensus that we're trying to build. And just to dwell on that in a little bit more detail, what those groups, what those organisations are actually doing, they are operating here on a data exchange basis. So we have given them access to the project, and in return, they have done a number of things for the project. First of all, they got involved way back at the earliest stages of the project. They reviewed the plan for the campaign, the equipment setup, the way that we were intending to process those data, and basically highlighted any problems that they foresaw at that stage. The idea being that they are then sort of bought into using the conclusions of that campaign and the data that comes from them in this consensus building process at the end. Before they had sight of any of the measured data, they have each run in-house blockage models, and they have provided reports on the outputs of those. And then we in the GloBE consortium, primarily Chris, who will take over in a second, has compared those model results with the measured data that we obtained through the campaign. And then we've gone through others that we can talk about today. That's about it for a very brief introduction from me. I'll hand over to Chris and let you talk about the model testing in more detail. Chris.
Great, thank you, Neil. Just in case anybody has any questions that pop into their head while I'm going through this material, there is a Q&A function which you can post the questions into. But during this session, I'm going to go through an introduction and a recap from the previous session, just in case anybody was not able to attend that, and just as a bit of a refresh. Then I'll go through the model comparisons onto the hypothesis testing, how we reach the conclusions, and then ultimately the final part, the accountancy and conclusions section. So starting with the recap. So in order to delineate the blockage of physics and therefore create an accountancy framework, we have a set of hypotheses that we need to prove or disprove. These were derived from a set of research questions that we defined during the project. I haven't actually presented those research questions, but just the hypotheses. From that, we can get a physics recipe, and from the physics recipe, we can get an accountancy recipe. And ultimately, as Neil's already said, this all goes into a joint statement, which is a public statement of all of the GloBE group, including the ITRG. But we'll go through that at the end of the presentation. So really, we have the the initial focus, which is on the measurements in the previous session. This was end-to-end of how we created the observations and the final data sets for wind speeds and the analysis of that. Some processing and initial analysis of the boundary layer height measurements. The processing of the NOTIOS MetMast and the floating LiDAR system data as the trusted reference for the confidence building. And also the processing of the wind farm SCADA operational data to form a pattern of production analysis. And we're bringing all that together now in the modeling stage to show how that has a bearing on the way we do the modeling. To go over the measurement campaign setup again, I'll go through these next slides quite quickly. Just again, as a refresher, we had 6 WindCube 400S scanning LiDARs operating in dual Doppler in a step-stair pattern with converging beams on the points in red you see on the map. We had a dedicated WindCube 200S for boundary layer height measurements, a floating LiDAR system in 3 locations, and 2 located with actual measurements from either the MetMast or the dual Doppler reconstructed point, and finally the MetMast itself, which is refurbished for high frequency sampling with ultrasonics. Once we completed all of the correction steps, which you can see in the bottom right-hand corner here, we're then left with these transects showing the wind speed ratios relative to a normalization point, showing the decelerations characteristic of an upstream induction, and also a downstream effect, which in this particular case, because it's 270 degrees, plus or minus 225 degrees, so 45-degree bin, it is an emergent wake effect. But we do see these characteristic decelerations. But once we narrow that directional bin down to 270 degrees and focus on this Cascasi gap measurement, we then saw the blockage-induced accelerations downstream. And that was quite a result for us, because that was able to lead us in the right direction for testing these hypotheses. I'll then go back to this animation, firstly because I love it, secondly because it includes an awful lot of information as a sanity check, both in terms of a pattern of production, so normalized power distributions from both wind farms, so we can see wake effects emerging on each of the wind farms from the other, but also emerging on the wind speed points, which have all been normalized by the points noted by the red star. And if I initiate the animation again, we go starting from southeasterly sectors, we go clockwise round to northerly sectors. And we see that as we get to the southerly winds, we get this U-shape forming, as some of the points are impacted by wake, but the ones further out are not. Then we get the downstream points from pair 4-7 being impacted by a wake downstream of NOTIOS. And then we're still seeing a bit of characteristic deceleration from these points upstream. So this is all making sense. The wake is then moved across Amram Bank. And then we get towards more westerly sectors where we see a slight wind speed ratio above 1 for the sector going straight through the gap. And this is for a 30-degree bin in this case. There is still a bit of wake impact on these downstream results. Then we get the wake effect again, and we continue around the entire windows as we get through to the north. Just to reiterate the pattern of production that we showed the last time as well, in terms of the impacts of power distributions as a consequence of boundary layer height. This is a 3-year concurrent period of SCADA data. And this is not using any of the data that was captured during GloBE, because we needed a longer term data set for statistical significance reasons. But this is actually pattern of production data filtered for a low boundary layer height range up to 400 meters. And key to note here is this power distribution across this lead row, and the tendency to increase power as we go further to the east. And this is indicative of a blockage effect because there are fewer turbines downstream of this corner turbine compared to this corner turbine. And we can see the impact of the boundary layer heights, because once we then increase the boundary layer height filter across these turbines, then that power distribution decreases in terms of its magnitude of variation across that lead row. So if we focus on these turbines once more, then we can plot this, remember that we have normalized by this point. And so we can create plots as a function of boundary layer heights and what that wind speed ratio is normalized by A01 in the corner. And we see a downwards track in terms of power ratio as a function of the boundary layer height. We also noted last time using these points purely upstream of Amram Bank West, using westerly sectors, so it's quite a wide bin this time, 60-degree bin plus or minus 30 on 270 degrees. This trend of decreasing wind speed ratio as a function of the wind speed itself. And this is indicative of the maximum thrust region imparting the most thrust force on the flow for the lower wind speeds as we would expect, which then diminishes towards a wind speed ratio of 1 once we get to the rate of power region where we get the reduced thrust. So this is all tying together to make sense as to what we expect the system to do once when we're trying to measure for blockage. Then we get back onto the hypotheses as a reminder. So we have these 5 hypotheses that we want to try and prove or disprove. Firstly, H0, there is no blockage effect at all, that it will be representative of the legacy approach, which is highlighted in this light blue box. Then we have that GB results in a downwards bias in AEP, which is the combination of the legacy approach and some sort of deceleration model. Then we have H2, H3, and H4, which are all very similar, all including upwards and downwards biases in AEP, or you could use synonymously power. However, H3 and H4 are separated by the boundary layer height has a large or small impact on the blockage effect. And those would be indicative of some sort of tightly or fully coupled modeling approach. So how do we actually use all of the measurements and the modeling together? We want to try and build a body of evidence from the wind speed measurements and those gradients and what impacts them, from observed power gradients and what impacts them, and any model results to separate the physics out. And we use our internal model, our VV or viscous vortex model, to assist in this process. So what best explains the observations that we are seeing? And the result of this question is a model physics recipe. So now I'll move on to the model comparisons, where we go a lot more in detail into the actual models themselves. Firstly, introducing RW's VV model. You see 4 models presented in this table. The first 2 columns are VV. The third is our RAN CFD capability. On the right-hand side is LES CFD from Palm from Fraunhofer-Eves. And originally, we put this plot together to demonstrate that we're getting decelerations and accelerations in a similar sorts of magnitude under certain atmospheric conditions from these 3 very different types of model, which operate at very different model orders. Palm is by far the most computationally expensive. But the first 2 columns show how VV is working underneath. First of all, you have an embittered part, which is the what you could say is the blockage part, where you capture these decelerations and accelerations in wind speed. You can see in the plots. And secondly, then we impose a viscous part on top as well, which is the weight component. So we tested this lower order model against the higher order models. The VV model doesn't have any specific tuning or wake model coefficient parameters to tweak. So it's not in there's no tuning process involved in the use of VV. And underneath it is an eddy viscosity model, which is very close to Ainslie, and a vortex model, which is Rankine half body. And it iterates towards the 2, and from that we derive a total turbine interaction loss. Now, we actually have a very fortunate position here within the GloBE project with our interaction with the ITRG, the Independent Technical Review Group. And as Neil's already said, part of that was an exchange, and the ITRG contributed model results for us to then bring together in a comparison exercise. So this will make use of the GloBE data with the ITRG or the Independent Technical Review Group models, and also conversations with them to get to this blockage physics and model representation, how we then do the accountancy and in this joint statement. And here we have a big list of the models that were included. So they are color coded, and I've tried to separate them down by the type of model that they are, the sorts of GB physics, broadly speaking, that they include. If a boundary layer height model is represented directly in the model itself, the range of boundary layer heights that would have been represented in the simulations, the range of stability conditions, and what the actual plot designation is. So this will be useful for you when you want to go back through this material later on. At the bottom, we have named our VV and CFD model explicitly for reference. So what we've used here, first of all, the wind speed measurements, but we're going to start with the pattern of production or from the SCADA data, operational data from the wind farm. So this was actually used now a 4-year long data set, and we filtered for wind speeds and directions from the lead row turbines, assuming that all turbines are 100% available and that there is 0 curtailment. So as close to representative of completely normal operation as possible. The normalized pattern of production is calculating using a lead row average. So the plots that you see, the pattern of production lines will all average to 1, but only from the lead row. And when you look at a wind farm overall pattern of production, that will be normalized by the wind farm average. So the average taken over the whole wind farm, not just the lead row. The models have been averaged directionally if the data was available over the same wind direction ranges, have been averaged across boundary layer heights if available, and have been averaged across stability conditions if available as well. So as an introduction to the sorts of plots we'll see, we can look at the very top right-hand corner is Amber and Bank West, and we're looking across this northerly row only during these comparisons. So 300 degrees plus or minus 5 degrees with a 7.5 plus minus 1 meter per second wind speed bin. So right on the high thrust part of the thrust curve, which brings out the most amount of signal in the noisy data. And we've run VV here on the plot on the right-hand side in 3 modes to represent the 3, broadly speaking, the hypotheses that we've tried to represent. The green line is that GBE does not exist. The brown line is that the partial GBE, so just operating in deceleration mode only. And the orange is the full GBE, so decelerations and accelerations. The blue line is the SCADA data. So we can already see that there is an asymmetric pattern of production across this lead row, which is not captured when you're not representing blockage. So what we'll do now is we'll go through the other models and add them to these plots. Because there were so many models provided, we broke the plots into 2. The measurements are actually the same results, just to be clear, but we changed the vertical scale on the y-axis in order to bring out the variations across the models. So the first thing that you'll see is that there's a broad variation in the model predictions. Some models predict almost no variation of power, and some models predict a far too great variation of power. Some models are quite smooth, and other models are extremely noisy. Some seem to make sense, and others don't seem to make sense. But these 300-degree direction, you could ask, well, how do we know that what we're seeing here is actually a real physical effect and not simply an artifact of the processing or of the underlying data itself? If we flip the wind sector to look at the opposite wind direction, 60 degrees, then we see that we get essentially a mirror image of the pattern of production across that lead row. So that gives us the confidence that we're actually seeing something real and physical in the data. Of course, the models have been run unless they're in a particular time series configuration for a real measured period. Then the models are all statistical, and we have to then, they're also discretized, so running discrete wind conditions, which is very hard to represent a broad range of conditions. However, generally speaking, the fully coupled and the tightly coupled models are performing pretty well, although not all models are created equal, and there's definitely a lot of noise here that we need to try and contend with. We can then broaden our investigation to not just look at the lead row, but look at the entire wind farm pattern of production. So in this instance, having completed the filtering, we then normalize individual turbine power by the wind farm average for that filtering condition. And we focused again on this magic 300-degree wind sector. What we can then do is plot the regression plots, a scatter plot of the measured pattern of production on the x-axis and the model's pattern of production on the y. And what we look for here is everything to be as close to the black line as possible. So with the R squared to be as high as possible and the gradient to be as close to 1 as possible. And we see here that we get quite a broad spread of results. All the models are captured here as well. So just take a note of the models that are represented here. Then I'll go through to the next set. And then we see again that there's quite a lot of noise in these results. Then we go to the next set. And finally, on the last 2 plots there, the center and the right-hand side, we have the RW's VV and RW's random CFD model. So generally speaking, the models all perform reasonably well. Some definitely perform better than others. One could argue that all models perform within the expected wake or turbid interaction model uncertainty, but there are some specific trends that I want to try and tease out. And notably, we have these global gradients. So if your wake model is predicting too little or too large wake, your overall gradient of your red line will vary away from the relationship of 1, which would be the black line. So typically one would then tune the wake model to best match the SCADA data or the operational data and get a gradient as close to 1. But we see something else that emerging that's very, very interesting. So if we focus on model C, this is a model that we know overestimates the blockage effect. And we included in the results here, even though we know it gets it wrong, because it illustrates a very important point. On the right-hand side, we have model D, which actually you see gets the global gradients is also slightly off, but you get these little sub-gradients that start to form within this overall pattern of production trend. So these sub or local power gradients form, and what does this actually mean? And how is the overall global power gradient also affected here? And we can use VV here to try and answer this question. So we ran VV for 300 degrees. We actually used an inversion strength, which is a parameter in the model of 1, which would, in theory, represent a hard lid, like the top of a wind tunnel. If we reduce that below 1, it becomes a diffusive lid, so a soft inversion, if you like. And this is the same underlying wake model in each case. So this is isolating an inviscid effect or interaction between the top of the atmospheric boundary layer and the blockage within the wind farm. So first of all, we look at 250-meter boundary layer height, and we see the very similar trend to what we saw in the model C from the previous slide. Then we increase the boundary layer height to 500 meters, then to 1,000 meters, then to 10,000 meters, or essentially infinity. And then we can replicate a very similar trend to model D that we saw on the previous slide. So what we can start to deduce from this is that the blockage effect and the boundary layer height interaction will create local power gradients within this global gradient. And this can be used to an extent to test how effective a particular turbine interaction, which would be where you bring together your wake and your blockage into one single overall turbine interaction effect, is performing. And we are fortunate at this wind farm location because we have a regular grid layout. If you have an irregular grid, these sorts of comparisons become quite difficult. And because we have a gridded layout, we can start to look at these non-orthogonal wind sectors where we start to see these very strong trends start to appear. So what we can see is that in the extremes, the blockage effects and the boundary layer effect as well can impact the global gradients, which can make it appear as an actual wake model issue, whereas in fact, it's down to the fact that either the blockage effect is not being included or included too much. So here we see, just to be clear about the plots, on the left of model C, we can replicate that behavior. On the right-hand side for model D, we can replicate that behavior. So a kind of interim conclusion here, just from looking at pattern of production, and this is somewhat outside of GloBE. One doesn't need a set of wind measurements to be able to do this. This can just be done by using ordinary SCADA data available from operational wind farms. The wake model will tend to change this overall gradient, the blockage effect, and boundary layer height / inversion strength all come together to then create these local subgradients. Now, overall, all of these things, when you're looking at multiple sectors and evaluating turbine interaction model performance, can just be classified as scatter. But what we saw at this particular wind farm location is a very strong trend. But they all contribute towards a streamwise power gradient and therefore scatter in these pattern of production comparisons. And just to reiterate the importance of the boundary layer height stuff here. Again, for the same 300-degree wind sector, and for boundary layer height range, the range of boundary layer heights, and inversion strengths are between 0.5 and 1. We see that we can quite strongly deviate from the measurements by either assuming that a very strong inversion or changing the boundary layer height. And the overall conclusion from this part here is that a blockage model must have some degree of atmospheric boundary layer representation, and a lot of care must be put into the inversion strength within that model as well, because you can over-represent the effects of blockage quite easily. And this was a learning for RWE during this project, and we implemented this lid strength option and use the data yielded from GloBE to actually investigate that further and add that parameter in. So that's the pattern of production, looking at just in terms of power. Then we can move across to patterns of wind speed. We have these 3 dual Doppler pairs scanning multiple points, therefore we get these wind speed gradients. and we can interrogate the model flow fields which were supplied by the RTRG group and compare them against the measured data, and then try and split out the hypotheses. And you'll see that similar trends emerge from the pattern of wind speed comparisons that you saw in the pattern of production comparisons. So just again to set the scene, we use VV to demonstrate these different hypotheses and these wind speed gradients. The measured data is in blue, so we get this characteristic deceleration. And then the different model representations are shown in brown, which is no GBE at all. So quite obviously, we need to include this deceleration component. But then we also have no GB upside, which is the red points, and the green points is the full accelerations and decelerations as model assumption, and you cannot distinguish between the two. And this is precisely the reason why we wanted to measure not just an upstream set of points and wind speed gradients, but also this wind speed gradients downstream of the Kaskasi gap and capture this acceleration. So in this particular case, we wouldn't be able to separate the different hypotheses when it comes to deceleration only or the full implementation of accelerations and decelerations. So what does this actually tell us when we look at the measurements from this upstream and downstream pair of the Kaskasi gap? Again, looking at the westerly wind sector, we get this slight more noticeable deceleration in the measurements than the model actually predicts. But on the right-hand side, crucially, the brown points again indicate no wind speed change whatsoever. And we do get a wind speed ratio of greater than 1, indicating some degree of acceleration. When there's no GB upside, so no acceleration components in the blockage model, we don't go above 1% in this case. And that could be considered unity because that type of model can only return to unity because there is no acceleration components in the model. And then once we get to the green points, we go above unity, which is where the actual measurements are. So this is a very important way of being able to distinguish between the models and the hypotheses. So once we then put all of these model results from the RTRG group onto this plots, again, we can see there's quite a large variation. We have on the left the pair 1, 2, and on the right pair 5, 6. The wind speed sector is a 45-degree sector in this case. It's quite a broad sector, which is why this wind speed trend looks as it does, because actually these points are being is normalized by this point. And so when you're coming from this wind sector from the southwest, it'll actually have a bit of acceleration on it here around the edge of the wind farm. So that's why we get this slightly odd-looking trend in the measured data set. And some of the models actually follow a very similar trend as well. But the deceleration upstream of Amaranth West is looking much more characteristic. This is now looking at a tighter wind sector for just the upstream pair of Amaranth West, so pair 5, 6. So 270 degrees plus or minus 5 degrees, and we see a very similar trend again. Some models getting the wind deceleration components a little bit too large, including RWE's RAND CFD model. Our VV model is sitting somewhere in the middle of the pack. And then we get some models that show very little change as well. So again, this is a good way of being able to see how all of these models and the southern model types are performing in this scenario. Then we can look at this pair where we have the pair 1, 2 and the pair 4, 7, which is upstream and downstream of the Kaskasi gap. Again, very similarly, as we looked at VV before, we can see where some models are getting a wind speed ratio too high downstream of the Kaskasi gap, and RWE's RAND CFD code is a case here as well, as is RWE's VV model in the way that we set it up here. And then a range of other models actually float somewhere around the middle. But crucially, one of the models that was provided to us from the RTRG group doesn't have any acceleration built into it. So is representative of VV with no deceleration or very similar. So we can consider this to be essentially unity in this range of models that we have here. So some models are actually going above the above this model line, the pink one, which is showing or indicating a speed up or an acceleration. All right, so what have we seen here as some little interim conclusions here from the model comparisons? Firstly, there's a very large spread of the methods that have been provided in the suite of ITRG models provided to us, and therefore there's a large spread of results. And the extent of this was actually a bit of a surprise. There are some models that perform very well and that some perform very poorly, specifically in the case of modeling the global blockage effect. The tightly coupled models, which exclude a boundary layer height representation, show negligible blockage effect impact, and therefore are of little value, including in an overall turbine interaction loss calculation, because they're not really doing anything. Tightly coupled models, which only contain a partial GBE or blockage, exhibit gradients which do not match the observations in terms of the accelerations above unity. And fully coupled models, the higher order ones, consistently perform the best when including the correct physics. And that's a very important point that I'll need to talk about a little bit later on. And the tightly coupled models with the good boundary layer height representation, including some sort of soft lid, perform very well as well, providing they're set up correctly. I've been using some terms here, which are the tightly coupled and fully coupled and decoupled. This is something I'll need to explain later as a naming convention that we developed within GloBE, and I'll need to explain towards the end, which is made clearer in the joint statement. So now we'll move on to the hypothesis testing and how we can use a body of evidence to show which hypotheses are true and which ones are false. So body of evidence number one, we have power gradients for unwaked and waked turbines that are only explainable when including blockage effect physics. That's pretty clear. The wind speed gradients upstream of the wind farm show deceleration only explainable by including blockage effect physics. And the wind speed gradients follow expected trends within the wind farms as well. So what does this mean when we go back to our hypotheses? That we can essentially confidently say that the hypothesis there is no blockage effect is disproven. The blockage effect exists, it's real. I think that might be quite clear now, given the progress the industry has made in parallel to GloBE running. However, it's an important point to cover. Body of evidence number two, the fourth point is that the wind speed gradients exhibit accelerations through the Cascadi gap that are only explainable when a blockage model includes acceleration. And what does this mean here? That model hypothesis one, that GB results in a downwards bias in EP only, is also not true. That's disproven. Body of evidence number three, the magnitudes of the power and wind speed gradients are only explainable when including an ABL representation. And I'll say that again, the magnitudes of the power and wind speed gradients are only explainable when including a boundary layer height representation. And number six, the range of potential power and wind speed gradients is large due to the impact of the boundary layer heights. That's something we've also been able to pull out of the model comparisons and just purely from measurements, that changes in the boundary layer height. And I'll say again, which I mentioned previously in the measurement session, that the boundary layer height cannot be separated entirely from other atmospheric stability effects, such as turbulence production, such as thermal conditions. And therefore, it cannot be treated completely independently, and you can accidentally get into a situation where you are changing boundary layer height independently of other atmospheric parameters, which should be coupled together. However, that remains a bit of a modeling risk at the moment. So what does this mean in terms of hypothesis 3 and hypothesis 4? That the geostrophic height or boundary layer height has a large impact on the overall blockage magnitude. Now, this does not mean, there's a point here in the grey box, that we have proven or disproven accountancy methods by proxy here, in terms of lead row correction or legacy methods or whatever. That's a very important distinction to make, and I'll come on to that later on. So we look at what this actually means in terms of how we would propagate that through to some sort of loss factor. So we can represent all of these hypotheses, as we have shown already, with the same underlying wake model using VV. And we can do this by breaking down certain wind sectors at Ammer Bank West and looking at how power propagates through a wind farm when running VV in these different modes of no blockage, decelerations only, and including accelerations and decelerations. And this is only for a single boundary layer height and lid strength at a wind speed of 9 meters per second. So if we pull out just this row of turbines that I've indicated in this box for a westerly sector, we can get some normalized pattern of production trends that will look familiar to anybody who's done a wake model or turbine interaction model validation before. And to an extent, why we arrived at this issue between model calibrations and lead row corrections in the first place, because we normalized to a turbine lead row turbine upstream. So if the lead, we do that, we normalize by this lead row, then this is the most productive, and all the downstream turbines along this row are less productive. And by using H0, H0, which is there is no blockage, we get this dark blue line. If we assume that there's decelerations only for H reference of H1, then we get this blue line here, this light blue line. And if we include both the accelerations and decelerations, then we start at a point where we've got less power at the lead row. But then as we go through the wind farm, actually we get an acceleration going through the wind farm, or an apparent acceleration. And this becomes true or more evident when you look at the plus on the right-hand side, which is simply normalizing these lines on the left by the dark blue line. And we see that we do get this redistributive effect from blockage introduced. And that's fundamentally underneath what blockage is doing to a wind farm. It introduces a streamwise power gradient. And the partial GB introduces a streamwise power gradient. They can only exist really below 1. There is one point here that goes above 1. But essentially, it would always be a downwards bias effect. So you're not capturing properly the full impacts of blockage if you're only assuming a deceleration. If we now look at the same row of turbines, but now from a northerly sector, we see here that the row of turbines here normalized by this row along the average. And then as we in the full GB is actually showing more production than the partial GB only, because some of that deceleration effect starts to be unwound. And when we normalize that out here, we then see that the full GB is actually slightly more productive. But this becomes more apparent. So the full GB introduces a small downwards bias for Amron Bank West, and the partial GBE introduces a large downwards bias for Amron Bank. If we look at the southerly sector, now this is a case where all the wind farms, except Kaskazi, because it wasn't operational at the time, have been included. And this is to illustrate the point that even though we are looking just at a single wind farm, we can never decouple fully the interaction on a blockage level between neighboring wind farms. As the proximity will increase between these wind farms, the effect starts to diminish, or at least that's what the models show. However, on a theoretical level, they will always be communicating with each other upstream and downstream on a blockage level. So what we can see here when we look at this row, first of all, this turbine is much more productive because there's fewer turbines upstream of it, which is why it spikes up. But the full GBE is more productive. The turbines are more productive when including accelerations and decelerations than when including no blockage effect at all, or just a deceleration component. And this is, again, when we normalize these lines out by the dark blue line, this is what we get on the plot on the right-hand side. This is upwards of 6% in terms of relative power, which is quite a lot. And this is why it's important to include these effects in an overall turbine interaction loss calculation, because how all of these effects sum up over the windrows, especially when your wind farm is located in a cluster of wind farms, will determine what overall magnitude or type of bias you have in your AEP assessment. So I need to actually add in some clarifications here about the hypotheses. What we have been proving and disproving here is related to the physics of, and what the physics of blockage actually does to wind turbine and wind farm power. So in other words, what we've managed to deduce is that the physics of global blockage has a redistributive effect of power within a wind farm with a cluster. In other words, what we have proven is that there is a power gradient induced by blockage relative to wakes only. And that's an important distinction to make, because the wakes only case is not representative of reality. Reality, we do have blockage, but what we run typically as wind farm developers and owners and operators are rapid models, which can sometimes be in wakes only mode, and that has traditionally what's been the case. And therefore, there has been either some sort of correction to account for the blockage required on top of a wakes only approach, or some sort of model coupling. So how do we actually deal with that? And that's where we need to move on to the accountancy section. So we have accountancy and some conclusions here now. And firstly, I'd like to bring everyone's attention to the joint statement on the blockage effect. The conclusions I will bring into the presentation now are consistent with the statements that we have made in this joint statement. And you can access this as a preview on the right-hand side, but you can access this by scanning the QR code, and is available on the Carbon Trust website. And this has been agreed across all of the GloBE partners and also the ITRG group, which is quite a substantial effort getting to that point. And I'll explain a little bit of how we go through this. So in the joint statements, there are a list of key findings. Key finding number 1 is that there is direct evidence of the existence of blockage, and that was observed in wind speed and power gradients at and around the wind farms. Key finding number 2, GBE, the blockage effect, decelerates wind upstream of and accelerates wind within and between wind farms. Consequently, the blockage effect has a streamwise and lateral redistributive effect on power within wind farms and clusters, resulting in negative and positive losses from turbine to turbine and from farm to farm. Key finding number 3, the blockage effect is sensitive to the thermal stratification and therefore a boundary layer height, including height or inversion representation, and that is required in order to correctly calculate the blockage effect magnitude. The impact of certain atmospheric responses, such as gravity waves, Coriolis, and shear on blockage-related losses should be further investigated, and not all redistributed energy may be recovered within a wind farm due to blockage. That's an important distinction to make. Key finding number 4, and I'm reading these out verbatim because it's very important to get the actual terminology correct here. GloBE has assessed a wide variety of industry models and accountancy approaches and identified significant variations in blockage, wind speed, and turbine power predictions. In order to minimize this blockage-related energy bias errors, the correct physics should be implemented and should focus on any of the modeling approaches. A set of modeling recommendations is proposed to narrow the modeling gap and thereby increasing the accountancy consensus. And this is the ultimate goal of GloBE, is to recognize and identify what the gaps are and use the GloBE data and modeling efforts to narrow those gaps and try and close them as much as possible. So when we move on to the recommendations, the GloBE project has developed a set of modeling recommendations in order to reduce the gap and variations in models' blockage-related losses. The output of all of these following methods is an overall turbine interaction loss inclusive of wakes and blockage, or GBE. So in the joint statements, the first page is covering the findings from GloBE. The second page is covering a detailed table of how all of these things break down. And you can see initially here that we have some the descriptions on the first column and model physics types and things. And we also have this naming convention of decoupled, tightly coupled, and fully coupled. So I advise that you read these through in a lot of detail as much as you can. However, broadly speaking, we have these 3 categories of decoupled, tightly coupled, and fully coupled. The idea of this is that each one of these methods can be used to capture these streamwise and lateral redistributed blockage effects into an overall turbine interaction loss impact on AEP. And it's also fair to say that because of the relationship between these types of models and the level of physics and the amount of computational expense, that they are going to be more or less heuristic. Now, the areas covered by the joint statements include a model description, a model and physics recipe, a GBE accountancy method, model validation prerequisites. Now, this is an interesting one because depending on how you are running the models and how you're combining them together, and how you are combining them and comparing them with operational data like SCAD data, like we've done today in this session, will determine how you then need to propagate that through in terms of a loss. And you don't want to be in a position where you accidentally double account or not account for blockage correctly. There is a series of important considerations on the models and the physics that should be included, and also a set of limitations on those various methods. And this should enable you and your organizations to map where your modeling and accountancy path sits relative to the other methods that are available in the market, and ultimately de-risk blockage. So a long time ago now, back in 2022, I presented this slide at Wind Europe, describing the motivation and the problem, and that there was an industry split. We had this lead row correction or redistribution or both question, which you can see on the right-hand side of this insert in the turquoise box. Now, I'm actually quite pleased to say that it is both. It is not one or the other. That fundamentally, the redistributive effect created by blockage is the underlying reason why a lead row correction or a fully coupled method to capture blockage is required. We have actually got to a position where we have reconciled these positions on the modeling and the accountancy requirements. And the last point there, that to provide a bespoke data set and for able to enable this consensus, mission accomplished. We've been able to get to a very good point in that, in my opinion, and it's something that we're very proud to be able to bring to the industry. One last point here before we go into questions is that the need for robust modeling is increasing, and the reason for that is larger and larger developments. This is taken from 4C offshore. This the developable areas in the North Sea, particularly in the Deutsche Bucht, and the amount of developable areas and the potential for blockage-related effects to impact from wind farm to wind farm is getting quite significant, and therefore the modeling requirements are increasing. And the big question is, therefore, how do any of these modeling approaches perform over significant spatial scales with many, many gigawatts of installed capacity? And that is something we haven't been able to address within GloBE. We've been able to address the underlying physics fundamentals, if not entirely, then a good way down the road. But there is this residual risk associated with modeling wind farms and entire wind farm clusters and these mega clusters over very, very large scales. But physics representation is ultimately the key, and that's what we've tried to break down within GloBE. But there are some questions remaining, research questions for further work. What is the impact of gravity waves on blockage power and AEP biases, and can these actually be separated out? Probably not, because of the way they fundamentally interact with your static and dynamic stability effects. What is the impact of Coriolis on the global blockage effect? And how does blockage effect evolve over these big, huge clusters? But that now brings us to the end of the technical material, and we can go back into some questions now. But before I quickly do, just like to one more time thank my colleagues for the assistance they provided over the many years that GloBE has been running. Without them, this wouldn't have been possible. It's a huge internal effort. And this is not covering the many, many tens of other RWE folk who made this possible from an administrative, legal, and operational perspective. I'd also like, again, to lay out some special acknowledgements to these individuals who contributed a huge amount to GloBE and provided us with the measurements data sets to get to this point. And also, this was all made possible through the Carbon Trust and the OWA Offshore Wind Accelerator Programme. So thank you to them and the partners and the public funding bodies. And additionally, because of the modelling effort that was put into the consultancy houses and institutions that you see listed at the bottom.
And thank you, Chris. A huge amount of extremely detailed technical work has gone into this. It certainly wouldn't have happened without you. So yeah, thank you for all your efforts. And I hope everyone in the call agrees that we've made a really valuable contribution here. I'm glad to say there are quite a few questions in the chat, quite a number of which relate to the interaction with the top of the boundary layer, which you mentioned a few times. Maybe a good place to start is sort of the simplest of those, which is, what is a soft lid, and how do you actually apply that in modelling?
So let's start the other way around there. What is a hard lid? So if we take a computational fluid dynamics scenario, you could model a wind farm within a computational domain, and you could represent the top of the atmospheric boundary layer by bringing down the top of the computational domain. And that would be representative of a hard lid. Either it would be a wall boundary condition, or it would be some sort of loose entrainment, but in any case, there would be an interaction with the top of that boundary. And that is not recommended to do in CFD that way because of the diffusive nature of the atmospheric boundary layer height. So when we then step down to a rapid model like our VV model, the wind farm is actually mirrored above the wind farm for the ground and also for the top of the boundary layer. And the wind farm is mirrored infinitely, actually above in each case. So by having a hard lid, which could be representative of some sort of very strong inversion because that's would be where the stable free atmosphere exists and has a resistive stability capping effect and prevents any vertical motion of the atmospheric boundary layer. That would then push down on top of the wind farm pressure field and increase the blockage effect. So that's how it's modeled in VV. And what we do in VV is apply a gain function to that to reduce the strength of that mirroring effect. So that's what's meant with a soft and a hard lid. And what that allowed us to do was actually bring down the boundary layer height inputs, which we can derive from a modeled source, such as WRF, by wind speed and by direction, like you would do for a turbulence input or a wind speed input, to more realistic levels, and still get the correct pattern of production and pattern of wind speed. So I said at the beginning that we don't have any tuning coefficients. That is true for the actual underlying wake model itself. But that is one parameter that we realized we had to add in. Otherwise, we could either have to put boundary layer height far too high, unrealistically high, to get the right pattern production, or introduce a soft lid.
That's great, thank you. You've sort of answered one of the other questions here, which was how do you know what ABL height to use in the modelling? I guess given some of the discussion in Tuesday's presentation on the differences between what was measured from the ABL LiDAR and the various modelled ABL sources, it might be worth dwelling on that a little further and saying if you're doing this in practice for a wind farm where you don't have ABL measurements for an on-site LiDAR, what do you do? How do you apply this knowledge?
That was one of the research questions that we had going into GloBE. Ultimately, if we think we had a suspicion at the outset of the project that the boundary layer height was going to be a crucial parameter. That's not something we measure. It's outside of our traditional means of being able to capture in a measurement campaign. It's certainly not available in a typical measurement campaign that you do for a wind resource assessment from a floating LiDAR. And thus you need a specialist measurement device like a WindCube 200 or 400S that has the powerful laser to measure at those heights. So the question was, can we use a model data source to do that? Multiple model data sources do exist, from reanalysis data, Error 5, down to wind research forecasting WRF levels. And from those, you do actually get a boundary layer height output as a quantity it varies in its definition depending on the PBL scheme used in those models. But broadly speaking, it's down to where turbulence decays below a certain threshold, or when your Richardson number decays to a certain point. Those different models have strengths and weaknesses, and that was what we tested by comparing them to the measurements. And on average, the measurements were slightly lower. However, in terms of boundary layer height over the measured period compared to those models. But the caveat to that is that what we were measuring is a parameter that's derived from measurements, taking into account vertical perturbations along the length of the beam when they tend towards zero, which is kind of a proxy for when your turbulence decays below a certain threshold, and also where your aerosol runs out. Because once your aerosol runs out, that's been generated from sea spray, you stop being able to get any sort of returns from the LiDAR. And your top of your boundary layer will typically serve to restrict the vertical propagation of those aerosols through the entrainment zone. So that those combine together. So it's quite difficult to compare on like-for-like terms between the measurements and the modeling. But in the absence of measurements every time on site, what we are using right now is a boundary layer height from WRF in a table of by wind speed and direction.
That's good, thank you. That also ties into the way that some of the model data are processed. So there's a question here about your VV results demonstrating the sensitivity of modeling model results to boundary layer height, and whether you've looked at binning model results by boundary layer height as well in the analysis that you've done, especially of the ITRG data, just your VV data.
Yeah, the ITI, so there was a certain resolution that the model results were provided in, and that was to an extent with knowledge of how particularly the high order models are run, unless they're run in full time series, where you couple it together with a weather prediction model and you get a full time series of all the atmospheric conditions. You have to run them in discrete cases. And the typical kind of operational production way of running CFD is that you would try and get some sort of long-term representative boundary layer profile, for example. And so we knew that we couldn't go crazy on the number of cases that we asked. Firstly, because of just a practical computational resource perspective and time perspective as well. So what we did is we asked to produce the results for some key boundary layer heights. And as you go up through the model order, it becomes increasingly difficult to prescribe what your boundary layer height exactly should be. But nevertheless, that's what we asked for. And then we just aggregated them together. So we approached it from that perspective, but I suppose the person who asked the question is correct that in an ideal world, we'd want to bin the data down by also the conditions that we ran in the models themselves.
So, finally, conscious we don't have too much time left, there are a couple of questions on the kind of practical implications of this for typical wind farms. You may well argue that these are the wrong questions to ask, so I'll let you push back on these if you want to. But there's one about the kind of trying to get a handle on the typical losses that you might attribute to blockage for a typical wind farm, so say a 500 megawatt wind farm, based on what you've seen here. And then there was another on sort of using what's come out of this to drive some better guidance on micrositing. So you're determining wind farm layouts and whether there's some general conclusions we can take from the data we've got here.
Yeah, so I'll take the second one first because the question has been raised several times about how does the blockage effect impacts wind farm optimization, layout optimization, and would you ultimately get a different layout by running a model that includes blockage compared to one that you wouldn't? And that's actually quite a difficult question to answer. One of the reasons we've struggled to answer that question internally at RWE is because the computational requirement from VV is actually a step up an order of magnitude greater than your traditional park models, which optimization is typically done on. The reason for that is because you bang through thousands of iterations of wind farm layouts to optimize. So that is a residual question. My gut feeling is that we wouldn't end up with layouts that are fundamentally different in some way compared to if we didn't include blockage. And going back to the first question, it becomes very tricky in the accountancy part to actually say whether wind farms on average would have a loss due to blockage. If we look at a decoupled method where you run a wake model and then you apply lead row correction style, in 95% of cases, I imagine, then that would always be a downwards loss purely due to the way what the lead row correction method is trying to represent, which is ultimately unwinding the positive side of the blockage effects, the positive unwinding effect going through the wind farm, that gets accidentally baked into your wake model validation when you're not including a blockage model. So that would always be downwards. And then the other question is, if you're using a model like VV, which is tightly coupled or fully coupled, you can't separate out the blockage and the wake. So you have to give up with that. But if you're looking at a tightly coupled method with VV, we can create an AEP with the blockage turned on and an AEP with the blockage turned off. And then we can itemize that in the losses sheet as to what the blockage effect actually is. But it becomes somewhat academic at that stage because one is not really interested in what the loss is without blockage. What the important thing to consider and to focus on is an overall turbine interaction effect, and your mechanism to get there you can determine by using that joint statement and map your way through that process. The one warning I would give to anybody who is doing these sorts of calculations is be very careful not to accidentally double account or under account in some way. But hopefully, I believe the joint statement will assist there.
That's great. We're out of time at that point. I would just again like to thank Chris very much for the presentation today. Refer you all to the joint statement again. If you didn't manage to take a screen grab or find a link earlier on, it's on the Carbon Trust website. If you look for Carbon Trust GloBE blockage, you'll find it from there. And feel free to get in touch with either of us if you've got questions. But at that point, we'll leave it there. And thanks very much for joining.